First thing we need to discuss is inductive reasoning. Inductive reasoning is something obviously you probably use every day, and this is more of a psychology type thing. Inductive reasoning is a reasoning that is based on patterns that you observe. If you observe a pattern in a sequence, you can use inductive reasoning to tell what the next terms in the sequence will be like. Here's an example of inductive reasoning. 2, 4, 6, 8, blank. Inductive reasoning. Each and every one of you in here is going to tell me that the next number in the sequence is 10, right? A conclusion you reach using inductive reasoning is called a conjecture. 10 is my conjecture. 10 is my guess as to what comes next. Not all conjectures turn out to be true. You can prove that a conjecture is false by finding a counterexample. A counterexample to a conjecture is an example for which the conjecture is incorrect. So, inductive reasoning is reasoning based on patterns, reasoning based on what we see has been true in the past. That's inductive reasoning. Let's say that 2, 4, 6, 8. On Monday, I give you $2. I walk in and I just hand you $2. On Tuesday, I give you $4. On Wednesday, I give you $6. On Thursday, I give you $8. On Friday, you're going to expect me to give you $10. But what if I walk in and don't give you anything? Okay? That conjecture was false. Okay, that was a counterexample because here's the thing. 2, 4, 6, 8, we know that logically 10 would follow, but does it have to? Is the question. No, it doesn't. Okay, so there's your inductive reasoning. Inductive reasoning can turn out to be not true. Conjectures are guesses as to what's going to come next. Counterexamples are things that it didn't work out that way. Write a conjecture. We know now what a conjecture is. Write a conjecture that describes the pattern in this sequence. Then use your conjecture to find out the next item in the sequence. Okay, follow-up visit. We go to the doctor. We're sick, and they say, well, after this visit, I want you to follow up in December, May, October, and March. December, May, October, March, ... And my question for you is, what do you think would be the next month in that sequence? August. Okay, is it every 5 months? Right. It looks like December to May, May to October, October to March. If this continues, then our next visit would be in August and August. Question though, does that have to be true? What if we only have 4 follow-up visits? Do you see where we're going with this? We would think that our next visit after that would be in August, or maybe they said, you know what, you're doing so good, then we're going to stretch it out. We're going to wait 7 months this time, or we're going to wait 8 months. Okay? So we know that conjectures could be false. Same thing, 10, 4, negative 2, negative 8. How many are we going down each time? 6, so that'd be negative 14 would be next, negative 20, negative 26, ... Okay. Conjectures. What's happening each time here? You're taking the middle out, aren't you? You got a whole triangle, and out of the whole triangles, you're simply removing the middle. Well, now I've got 3 whole triangles. Now take the middle out of that. Now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 whole triangles. So the next item, the next piece in this series would be just take the middle out of all of these. Now, y'all can see, I'm not going to finish that, but that would be what the next one would look like. And the triangles are getting smaller and smaller and smaller. Okay. Next up. Make a conjecture about, and I like this problem, this is a good one. Make a conjecture about each value or geometric relationship. List or draw some examples. Okay? You're going to have to do some examples here. The sum of 2 odd numbers. We're going to use inductive reasoning to try to figure out when you add 2 odd numbers together what happens. Even numbers. Let's see. She says even numbers. When we add 2 odd numbers together, we'll always get an even number. I don't know. We need examples. 7 plus 3. 10. 8 plus 1. Oh, that's not odd. Right? Now, sometimes our conjectures could be wrong, because let me show you something. 5 plus 5, 10, we did 3, 5. Maybe I did these 3 examples, and I started looking, and I say, hey, when I add 2 odd numbers together, I always get 10. You need to continue. Okay, you need to try a wide range of examples, because if my first conjecture was I always get 10, well, there's a counterexample. So then we continue on, we try some more, and we see that anytime we do add 2 odd numbers, we get an even number. That is inductive reasoning. Later on, when you get to your higher maths, we actually did a proof of this, to where, now I'm getting off on the other. If you prove it, not by examples, because honestly, how many examples are there? Millions upon millions of examples here that we could test. How many examples do I need to prove that this is false? 1. And if there's millions upon millions of examples that I've got to check out, well, I only need 1 to prove that it's false. So, inductive reasoning is not the best method. There's another method called deductive reasoning that we're about to get into. Deductive reasoning is actually proof by, or reasoning by proof. So this is inductive. Here's a go. Find a counterexample. This will make you think a little bit. Find a counterexample to show that each conjecture is false. N is a real number. You might know of many numbers that aren't real. You're good with real numbers. That's all your numbers. Okay? All the numbers that you've dealt with. Later on in Algebra 2, pre-calculus, you'll talk about numbers that are not real. You know what they're called? Imaginary numbers. Okay? But that's to come. That's to be continued. But for now, real numbers, all the numbers that you've dealt with. N is a real number. Then we're saying that n squared will always be bigger than n. And what it says is find a counterexample of that. Is that true? For any number, if you square it, will it always be bigger than the original number? Does anybody have a counterexample? 1. If you plug 1, if you pick the number 1, is 1 squared bigger than 1? It's not. Now what if I put this? Would it be true then? Yeah. Was there another counterexample that would work besides 1? There's one other one that I can think of, 0. Is 0 squared bigger than 0? No, but now it would be true. Now, here's my thought. I want y'all to say, is that true then? Because that works for 1 and 0 as well. Now just going a step further with it. Will that always be true? What about 1/2? What? Somebody tell me what 1/2 squared is. Multiply tops and bottoms, you get 1/4. Is 1/4 bigger than 1/2? No. No. So that would be some more counterexamples that works for doesn't work for fractions either. This one's tough. Nobody ever gets this one. Okay. See what you can do with it. Find a counterexample to show that each conjecture is false. If JK is equal to KL, then K is the midpoint of JL. And I can draw this right here, and I can make you think that that is true. If JK is equal to KL, if JK is equal to KL, does that not mean that K is the midpoint? I'll give you a second thing. He says, what if it makes a right angle? Where's K at there? What are you saying about K? Right here? What do y'all think about that? If JK is congruent to KL, is K the midpoint? No. That is not a line segment. Okay? So here's another example you can do. You can do a triangle. What kind of triangle would that be? Y'all remember that? From two sides. JK is the same thing as KL. Isosceles. Remember that? If JK is the same thing as KL, will K always be a midpoint? No. If they're collinear, If I threw that in, if JK is equal to KL and they are collinear, then K is the midpoint. Yes, that is true. Next topic, conditional statements. Need to know this definition. A conditional statement has two parts, a hypothesis and a conclusion. There's some more words that you need to know. And what you can do, you can actually write it like this. This is an example of a conditional statement. A lot of times conditional statements are called if-then statements. If it is raining, then I'll carry an umbrella. You use conditional statements every day. Okay? Under what conditions will something happen is what a conditional statement is. If this happens, then this is going to happen. If it is Monday, then I'm going to wear my bow tie. Okay? The condition is being Monday, then what's going to happen? I'm wearing my bow tie. If it is noon in Georgia, then it is 9 o'clock in California. Each conditional statement has a hypothesis. The hypothesis is the if part. Each conditional statement also has a conclusion. That would be the then part. If you remember in science, a hypothesis is like an educated guess. If this is going to happen. Okay, that's your if part. The conclusion is what happens as a result. That would be your then part. First problem. Rewrite the conditional statement in if-then form. The conditional statements are 2 points are collinear if they lie on the same line. If-then form means I want my if first, I want my then second. So here's how I'm going to do it. 2 points are collinear if they lie. Well, notice there's already an if in there. So let's write it like this. If. Now you got they. Think back to English. I want my subject here to go first. So I'm going to put, instead of they, if 2 points. If 2 points lie on the same line, there's my if part, then, finish it. They are collinear. I think I might have an extra L in it. I thought it was just one. Now it's in if-then form. If 2 points lie on the same line, then they are collinear. Now if I ask you, Sierra, what's the hypothesis? There you go. 2 points lie on the same line. And Sierra, what would be the conclusion? They are collinear. Hypothesis, conclusion. Write your hypothesis first, your conclusion second. Next problem. All sharks have boneless skeletons. You know that? All sharks have a boneless skeleton. How in the world are they boneless? I don't know, we'll have to investigate that. I think they're skeletons that are made of cartilage. There's no bone there. Yeah, they don't have bone. So it's going to be hard to punch it in the nose and break its face. I don't think it's made of cartilage. I think they've tried to dodge it. But anyway, all sharks have a boneless skeleton. Because we wanted an if-then form. This one's a little tougher. Some of these make you think a little bit. Let's try this. If an animal is a shark, comma, then what's going to be true? There you go. It has a boneless skeleton. If an animal is a shark, then it has a boneless skeleton. If-then form. You have your condition, which would be, it's a shark. You have your resultant or your conclusion, which it has a boneless skeleton. A number divisible by 9 is also divisible by 3. We'll just talk about the rest of them. You got you a couple of good examples there. I would put on this one, if a number is divisible by 9, if a number is divisible by 9, then it is also divisible by 3. That was pretty easy. Conditional statements. Now we're starting to tie these things together. Conditional statements can be true or false. To show a conditional statement is true, you simply present an argument that the conclusion follows all cases. Not in most cases, but it must follow all cases. To show it's false, then, you need a single counterexample. To show that a conditional statement is false, you need simply one counterexample. Let's try here. Write a counterexample for this. If x squared is 16, and let me show you another way they might write this sometimes. If x squared is 16, then, and they'll put an arrow there, x equals 4. Or they'll say it like this. X squared equals 16 implies that x equals 4. So I need a counterexample. If x squared is 16, well, does x not equal 4? I thought it did. Is x equal to 4, or could x be 4? Can somebody come up with another example, or an example of what would make that false? Because I'm saying x squared is 16, I know that x is 4. Do you know x is 4? Or could it be, what else? Negative 4. There's your counterexample. X doesn't have to be 4. X could be negative 4. So there's the counterexample of, you can't say if x squared is 16, then x is always 4, because it could be negative 4. That's your counterexample that proves that wrong. Next one says, show that this conditional statement is false by finding a counterexample. If it is February, then there are only 28 days in a month. This one's pretty obvious, right? Does February always have 28 days?
No.
What year?
Leap year.
Leap year. And that's your counterexample. Counterexample, and I'm going to write it like this. We'll call it a CE, counterexample. Colon, leap year. As we know, in leap year, there are 29 days in February. A conditional statement, I've already told you this. A conditional statement can be written in the form P implies Q. You can ask your grandparents, I'm sure they remember a lot of time the whole mind your P's and Q's. There used to be an old saying years ago. Could possibly come from this situation. A conditional statement can be written in the form P implies Q. So where examples of that? If it is raining, that implies that I'm going to carry my umbrella. Okay, P implies Q. A converse. Does everybody know what a converse is? It's a shoe. That's correct. It's a shoe. You know what it is mathematically. A converse in math. Prefix con, or let's see. How could we remember this? Converse. I used to have a way to remember this. But to find the converse of a conditional statement, notice what we changed to. And here's all you have to put. Don't write all this stuff down. Conditional statement, P implies Q. The converse, you flip your Q and P, your P and Q. So to find the converse of the statements, you simply switch P's and Q's. So my original statement was, if it is raining, I'm carrying an umbrella. The converse of that statement would be, if I carry an umbrella, then it is raining. Is that always true? Let's say that my conditional statement were true. If it is raining, I'm carrying an umbrella. So with that said, if I carry an umbrella, does that mean it's raining? Did I say the only time I'm carrying an umbrella is when it rains? I didn't say that, did I? I said if it's raining, I'm carrying an umbrella. What if I just have a favorite umbrella that I like to carry around everywhere I go? And if it's raining, I'm going to carry it, but, well, it's not raining, I'm carrying it too. So will the converse always be true? If I carry my umbrella, then it's raining. No, it's my favorite umbrella, and I just like to carry it around. So therefore, a converse is not always true. Inverse. These little squiggly lines are called tildes. Okay? They mean not. To find an inverse, the inverse is not P implies not Q. Okay, P and Q. If it is raining, then I'm carrying my umbrella. The inverse of that is if it is not raining, then I will not carry my umbrella. And I told you it's my favorite umbrella. Okay? So if it is not raining, I'm not carrying my umbrella. Given the conditional statement is true, does that mean that your inverse is true always? No. Could be. But your converse and inverse do not have to be true. Your contrapositive. The contrapositive is not Q implies not P. So what you did is a contrapositive is kind of a converse and inverse put together. You not them both and you switch them. My original conditional statement, if it is raining, I'm carrying an umbrella. The contrapositive of that is if I don't carry my umbrella, then it is not raining. Is that always true? That hurts your head a little bit. If it is not raining, okay, if it's raining, I'm carrying my umbrella. What if I don't carry my umbrella? Does that mean for sure that it is not raining? Yes, because I told you, if it is raining, and I'm a man of my word, if it is raining, I'm carrying my umbrella. Well, what if that day I did not carry my umbrella? Is it raining outside? No. So, question, is the contrapositive always true? Yes. When you have a conditional statement, the converse could or may not be true. The inverse could or couldn't be true, or the contrapositive is always true. I would know that. If a conditional statement is true, the contrapositive will also be true. The converse and inverse could be. Write the converse, inverse, and contrapositive of each conditional statement. My conditional statement says two angles that have the same measures are congruent. Is that true? Yes. Two angles have the same measure are congruent. So my conditional statement, I'm going to write it like this just so I don't have to put the whole thing. Same measures imply, there's your symbol for congruent. Equal sign with the tilde over the squiggle. Your conditional statement, if two angles have the same measures, that implies that they are congruent. If, that's your hypothesis, then that's your conclusion. And we're asked to find the converse, the inverse, and the contrapositive. Let's start with the converse. Nicole. Converse, you simply switch them. Your original statement was, if two angles have the same measures, then they are congruent. Now flip-flop those and tell me what the converse of that would be. If two angles are, then they have the same measure. And my question for y'all, can you come up with a counterexample to that? Is that always true? If two angles are congruent, think about two congruent angles. Picture those angles. Try to picture all of them. Will they always have the same measures? Yes. Okay. So here my converse is true. Does it have to be true? Not always, but here it is. Inverse. Now to find the inverse, Hunter, we need to go back to the original. My original statement, if two angles have the same measures, then they are congruent. The inverse of that, we'll have to throw those knots in there, right? If two angles, what, Hunter? Now, I'm going to put not the same measure. If two angles do not have the same measure, then, Hunter, they are not congruent. And inverse simply negates the first, negates the second. If two angles do not have the same measures, picture two. You have a 30 and a 60 degree angle. You have a 20 and a 30 degree angle. Are those two angles congruent? No. So is the inverse true? Yes. And finally, we have the contrapositive, which we know will be true. I'll call it a CP, contrapositive. And I'll do it for you. We're kind of combining the two. We take the inverse, we take the converse, put them together. We got to negate it, and we got to flip it. And the way I'm going to do that, I'm just going to take my inverse and flip it. If two angles are not congruent, then they will not have the same measure. And we don't even have to think about that because the contrapositive will always be true. A biconditional statement. Okay, we're done with conditional statements. Now let's talk about biconditional statements. And this is a lot of math terms that I'll explain in just a second what it means. A biconditional statement is the conjunction of a conditional statement and its converse. What that means is it's the conditional statement and its converse put together. It works both ways. And a lot of times they write like this. Let's take the last example. The last example was a biconditional statement because it worked forwards and backwards. If two angles have the same measures, they're congruent. If two angles are congruent, they have the same measure. That's a biconditional statement. We can write it like this. Biconditional. Since we know it works forwards and backwards, if two angles have the same measure, then that implies they are congruent. And if two angles are congruent, then that implies that they have the same measure. Put an arrow on both ends. It works both ways. It's a combination or the conjunction between a conditional statement and its converse. The converse is the other direction. That's called a biconditional statement. It works forwards, it works backwards. Here's the example that they gave. Samantha is elected by the district coaches. Samantha is named to the All-Star team. And if we know that if she's elected by the district coaches, then she'll be on the All-Star team. And we know that if she's on the All-Star team that she was elected by her district coaches, then we can write that as a biconditional statement. Notice they have the double-sided arrow there. One means the other, they're one and the same. One implies the other implies the one. Okay, forwards and backwards. An abbreviation for this. And we know that if one implies the other, and that's the only way, okay, we can write that as an if and only if statement. Okay, let's go back to the other one. Let me show you what I mean. Scroll down. If two angles have the same measure, that's the only way, correct me if I'm wrong, that's the only way that they can be congruent. If two angles have the same measure, that is the only way they can be congruent. That's always true for biconditional statements. Two angles have the same measure, or let's write it backwards. Two angles are, and you can do it either way, two angles are congruent if and only if they have the same measures. Would y'all agree with that? Two angles are congruent if and only if they have the same measures. Is there any other situation where they could be congruent? Anytime that you have a biconditional statement, you can throw in that if and only if. That's the only way it can be true. It's true if this is true, and that's the only way it can be true. And the abbreviation for if and only if, and a lot of you are going to see this, especially if you dozed off the first part of the lesson, you're going to see this abbreviation, you're going to say, Mr. Smith, you misspelled it. No, I didn't. The abbreviation for if and only if is IFF. Okay, if and only if. So anytime you see IFF, you know that that is a biconditional statement. You know that it works forwards and it works backwards. It's true forwards and it's true backwards. Now let's take a look at some biconditional statements. Here's one. Write each biconditional, it tells us it's a biconditional. Write each biconditional as a conditional and its converse. This biconditional says an angle is a right angle. Notice that if and only if. Its measure is 90. The only way an angle can be a right angle is if it is a 90 degree. That's the only way. So let's write it as a conditional statement. The conditional statement is an angle is a right angle. It implies that it's a 90 degree angle. And it also wants us to break it into its converse. The converse of that would be if it is a 90-degree angle, then it's a right angle. And since we know it's a biconditional, I know both of those are true. The only way it can be a 90-degree angle is if it's a right angle. The only way it's a right angle is if it's a 90-degree angle. It works forwards and backwards. That's the only way. The conditional statement's true. The converse is true. It is a biconditional. Now, is this a true biconditional? Yes. Yes, that's the only way it can be a right angle and forwards backwards. This is a true biconditional. Now, could I have a false biconditional? Could I be falsely tricked into thinking something's a biconditional? Maybe so. Let's see. Write each biconditional as a conditional and its inverse. Converse. Okay, conditional statement. This is true if and only if this is true. So x is greater than -2 implies that x is positive. In order to be sure, let's check its converse as well. X is positive implies that x is greater than -2. Now let's start with the second one. X is a positive number. Think about all. Notice I throw in that word all, because it must be true for each and every one. X is a positive number. Does that mean that x is bigger than -2? What do y'all think? What do you think, Cole? If x is a positive number, is it bigger than -2? Think about all your positives. Is it bigger than that? Yeah, true. In order to be a true biconditional, though, they must both be true. Now let's check the first. X is bigger than -2 implies that x is positive. So Jordan, D, think about all the numbers bigger than -2. If you pick a number bigger than -2, does that mean you picked a positive number? No. What's your counterexample there? -1. Is -1 bigger than -2? Yes. Is -1 a positive number? No. Just because a number is bigger than -2 does not imply that it's a positive, so that is false. So this biconditional would be false. Right, each biconditional, same thing. Two angles are complements if and only if. Okay, conditional statement. Two angles are complements. I'm just abbreviating here. I don't want to write the whole thing down. If and only if the measures have a sum of 90. The converse of that, we're going to test to see is it a true biconditional. If it has a sum of 90, then that implies that they are complements. Rachel? If two angles are complements of each other, do they have a sum of 90? Yes. Destiny. If two angles have a sum of 90, are they complements of each other? Yes. So therefore, guys, is this a true biconditional? Yes. It works forwards. It works backwards. I can actually throw in that if and only if. It will always be true, or you can put if and only if, or you can put arrows. It is a true biconditional. Last one. There's no school if and only if it is Saturday. You already know this one. You think through it, and you already know, is this a true biconditional? What do y'all think? No, it's not going to be. Your conditional statement, I do want to do it because of this practice here. No school implies it's Saturday. The converse would also have to be true. The converse would be if it is Saturday, then that implies there's no school. But is it a true if and only if statement? The second one, if it's Saturday, there's no school. We know that. Well, unfortunately, sometimes we lay out too much. If it's Saturday, there will be school. Right? But on the other hand, if there's no school, it doesn't mean there's Saturday. No, it could be Sundays, it could be holidays. That's false. So this biconditional, since you have a false, it's not true this direction, this biconditional would actually be false. Works one way, possibly, like I said, unless you count savings. Works one way, but it does not work the other way, so this is a false biconditional.